Hello, and welcome to this video discussing RTL for the programmable NoC, or as we call it, the modular NoC for short. The primary purpose of the modular NoC is to bring NoC capabilities to RTL designs. This is part one of a series of videos where we'll walk through our solution. The agenda is as follows. First, we'll start the conversation by discussing some of the challenges facing developers using our current solution. Then we'll provide an overview of the modular NoC solution by introducing the three main steps needed to incorporate the modular NoC into your RTL. Next, we'll give a brief overview of the test cases we've targeted for this release. And finally, we'll introduce the topics that will be discussed in the remaining videos in this series and share the location of the tutorials and example designs that you can try for yourself. There are several challenges that exist with our current NoC solution. From the beginning of the Versal Adaptive SoC, the NoC IP was developed as an IP integrator-only IP. This requires all instances of the NoC IP to be placed on a block design canvas. Let's consider the effects of this decision. In the lower left-hand corner of the gray BD, you see a box labeled Team A. Assume this is a group of RTL developers that would like to utilize the NoC to communicate between IP1 and IP2. To achieve this with our current flow, the Team A developers would need to route both AXI buses from IP1 and IP2 to the BD and connect through a NoC IP. Routing these AXI buses through the RTL hierarchy is a tedious process. Now let's assume a second team, Team B, also wants to use the NoC in their design. They also need to route their AXI buses from IP3 and IP4 to the BD and connect them with the NoC IP. In this case, the BD becomes the bottleneck. Every time there are modifications to the NoC connectivity or attributes, the teams would all need to update the block design. Additional complications arise when you consider DFX use cases. The modular NoC solution resolves these issues by allowing the NoC to be distributed among various design sources and hierarchies and even between teams. The modular NoC solution is comprised of three main steps. Step 1 is to connect all AXI buses that want to utilize the NoC to Xilinx Parameterizable Macros, or XPMs. The master XPM contains the NMU to get on the NoC, and the slave XPM contains the NSU to exit the NoC. These XPMs are stitched into the custom RTL manually anywhere in the design hierarchy. In this manner, Team A and Team B can each specify their XPM NMUs and XPM NSUs in their designs independently, and they no longer need to update a shared block design. The second step of the process is to add constraint files, or XDCs, to the design that define connectivity and quality of service parameters for each individual NoC connection. Scoping these XDCs to a level of hierarchy also allows Team A and Team B to work independently. The final step of the flow is to execute the validate NoC command. This new command ensures full connectivity between XPM instances, runs DRCs, and executes the NoC compiler to generate the NoC solution for the design. This command can be called explicitly by the user to check their design, or will be called implicitly by the flow. Using this process, teams can develop their solutions independently, and the tool will ensure that the NoC is not overcommitted. Modular NoC addresses all the issues discussed in the previous slide, and it maintains compatibility with our current solution. Although hardened resources must still reside on an IPI canvas, connectivity between RTL NoC XPMs and BD NoC resources can still be achieved by creating NoC connectivity through XDCs. Simulation and debug flows, as well as Vitis Unified IDE and system software support, are unchanged since they occur after the NoC is aggregated during the validate NoC command. Finally, this solution is designed with enough flexibility that it can accommodate future enhancements such as security and isolation features. Let's quickly walk through these steps to ensure your understanding. The SIPs and the NoC IPs still need to be on a BD and incorporated into your design. The NOC IP contains the hardened memory controller and is still only available on the BD canvas. We'll call this BD the System BD. Now let's assume we have an AXI DMA in the PL that wants to access this memory controller. The first thing that we would do is to find the AXI memory mapped bus coming out of the DMA memory controller in the RTL. We would attach an XPM to this AXI bus. The XPM templates are available in the Vivado IDE under the Language Templates. You can copy the language template into your RTL and hook up the AXI bus from the DMA to the XPM NMU. The header of an XPM is parameterizable such that you can match the AXI parameters of the DMA, such as the data or address widths. There are a few other parameters, like NOC fabric, enable user interrupt, and sideband pins that you can optionally enable on the XPM. These will all be thoroughly documented in the user guides. Once we have the XPM connected to the DMA AXI bus, we can move on to the second step. The next step is to make the NOC connections between the NMUs and NSUs. The XDC file can be specified per module and does not require the RTL to be elaborated when modified. Looking at the example file here, the first two lines store the NMU and NSU instances into Tcl variables. These are given paths to NMU and NSU instances. In this manner, the command can be applied to the NMUs and NSUs contained in either the XPM modules in RTL or the NOC IP in the BD. It does not matter how the NMUs and NSUs are added to your design. In the example we've been describing, the NMU would be in the XPM module connected to the DMA in the RTL, and the NSU would be contained in the DDR memory controller within the NOC IP instance on the BD. The next line defines the addressing aperture of the NSU. The base address and range is used by the NOC compiler to ensure that all addresses contained within this aperture are routed to the appropriate NSU. Note that if the NSU is located on the BD, the aperture of the NSU is defined on the BD and would not need to be specified in the XDC file. The next line creates a NOC connection between the NMU and the NSU and stores it to a variable called NOCCon0. Finally, the setProperty command provides all the QoS properties related to the connection. With this XDC, we found the NMUs and NSUs in the design, created connections between them, and applied the QoS constraints to those connections. So how does this all get aggregated together? We've created a new validate NOC command that can be run explicitly by the user. This command will find all NOC instances across any design source, including BDs, RTL, DCPs, or even EDIF sources. It understands the connections between NOC instances and QoS requirements regardless of whether they originate from a BD canvas or an XDC file. The command also executes design rule checks to ensure that the design is fully connected with no dangling NOC instances. Finally, it invokes the NOC compiler and displays the result in the NOC view. The standalone command enables users to iterate on a NOC design until they have all the parameters correct. However, when it comes to integrating the command back into user-run scripts, it is not really necessary. The NOC validation is handled by the standard Vivado flow. When users run synthesis in either project or non-project-based flows, the validate NOC command is automatically invoked. It is also run during link design and place design. For now, the final NOC solution is completed during placement. In the future, this may be augmented to support a post-route ECO flow. Let's put this all together. Starting with the BD on the right-hand side, you can see the SIPs with a NOC IP containing a hardened DDR memory controller. In the top RTL on the left, you can see an AXI master attached to an NMU XPM inst RTL. Contained within the XPM is the NMU egress onto the NOC. The XDC file at the bottom connects the NMU in the RTL to the MC port 1 of the NOC IP on the BD. Finally, the QoS properties for this connection are added at the bottom of the XDC file. In this manner, extending the NOC into user RTL is pretty straightforward. A few things to discuss before we wrap up this video. Let's look at the supported use cases for 2024.2. Starting in the upper left, this is the use case we just discussed. An AXI master in the RTL accessing a port of the DDR memory controller on the block design. If we move to the right, you can also have a master on the BD access a peripheral in the RTL. In this case, the processing subsystem contains a master that is connected to the NOC IP on the BD canvas and uses the modular NOC to connect to the slave in the RTL. In the bottom left, you can have an RTL master access peripherals of the processing subsystem, perhaps an AXI master accessing the on-chip memory of the processor. Finally, in the bottom right, the modular NOC enables RTL to RTL NOC transfers. In this case, both the master and the slave are in the RTL and can be connected without touching the BD in the design. DFX use cases will be discussed in future videos. Now that you have an overview of the modular NOC solution, let's go over the rest of the videos in this series. The next 3 videos will walk you through adding the modular NOC to a design one step at a time. First, we'll add the XPMs to the RTL, followed by editing the constraints file, and finally running the validate NOC command. Each of these will contain a demonstration showing each step in detail on an example design. After this, we'll have a video introducing how the modular NOC intersects with the DFX flow. This will introduce the concept of a virtual NOC interface and describe how we break the NOC path into 2 segments on the DFX boundary. Finally, if you want to try the modular NOC, we have a series of tutorials you can download and run. The first tutorial is the foundational tutorial and introduces all the concepts. The second tutorial addresses the basics of DFX, the third tutorial covers advanced NOC properties, the fourth covers advanced DFX topics, and the final tutorial covers HBM. For more information on the tutorials, please refer to the README file on GitHub.